Hi everybody, how are we doing today? We'll talk about two vector operations today, which are grounded in calculus. That is curl and divergence. Okay, so let's discuss that, curl and divergence. For that, let's review a gradient. What do we remember for a gradient? Some of you people didn't remember that on the exam 3, but gradient applies to scalar functions, right? We can take a gradient of a function of 3 variables, and we'll receive as an output a vector. So a vector with 3 components. What are the components? Of course, partials, right? Partial f with respect to x, y, and z. So today we'll look at it in a little bit an abstract fashion. We'll think of it as a vector. We'll understand gradient indeed as a vector, as I was occasionally drawing an arrow on the top. But today we'll really understand it as a vector. And we will understand that this vector is written next to f, and f is understood as a scalar. And usually we do write scalars in front of vectors, but since we think of this gradient vector as being applied to f, then we will write it on the left. So if we want to think then of a gradient as its own separate vector, then we will write it symbolically in components like this, dx, dy, and dz, and then apply it to f. Or if you wish, we can write it as a vector in components I ddx plus j dy, or if you insist on writing components in front, ddxi plus ddyj plus ddzk applied to f. So then if we can think of it as a vector, so gradient is ddx. Let me write like this. Sometimes you see this notation as well. Plus k dd z. Then you can start thinking of all the vector operations that. How about a cross product? So indeed, curl will be related to a cross product, and divergence to a dot product. So we will introduce these two operations today. We will calculate simple examples, and we'll announce some physical applications without real explanation of why they describe certain physical behaviors, because that will take some further development in the next classes, in the next week or so. So cross product. For cross product, of course, we have to have another vector, and this another vector will be just a vector field. So writing it like that, we will have a cross product of a vector consisting of these differential operators and a vector field. And divergence will be a dot product with a vector field as well. Dot product with a vector field. So here you have partial x, partial y, partial z, cross product with, usually we would write for components of f, p, q, and r. And here we'll have dx, dy, dz, dot product of PQR. All of this understood as functions of three variables. For instance, P is a function of X, Y, and Z. Good. So let's move on to an example. So before an example, let's look at this formula for the curl. So that may be a little strange if you look at it first time and wondering, okay, how am I going to remember this complicated formula? But notice what you have in the last component, dq dx minus dp dy. That's the familiar integrand under the double integral in Green's theorem. So that should get you thinking of the relationship with the Green's theorem. And indeed, we'll develop it later. But first, how do you remember this formula for the curl? Well, since we already said that the curl of f, I will write it like this. Sometimes and sometimes we'll write it like that, is just the cross product of the vector consisting of partial derivatives with f. Then we will just apply the formula for the cross product. So the cross product in components is best understood like a determinant of the matrix, where for the second row in this matrix, we'll just write the formal partials, dx dy dz. So then what happens if we take the determinant? So the first component will involve this determinant. So we'll have dr dy minus dq dz. For the second, we will have minus j and then determinant of dx dz. We have p and r. And finally, we will have k times the determinant of partial x, partial y, pq. So this last one is the familiar dq dx minus dp dy from the Green's theorem. But that's only because in the Green's theorem, we were looking at a vector field which was defined on the plane, so the third component was equal to 0. Okay. So these are the two ways to think about the curl, as this vector in components or as the determinant of this matrix ijk partial x partial y partial z components of f, p, q, and r. Good. So let's do a simple example. We want to find the curl in this case where our function is given as xz, xyz, and minus y squared. So we want to find the curl of xz, xyz, and negative y squared. What is it equal to? Well, take a pause, try to calculate yourself. After you come back, take a look at this. So we'll have to do the cross product with our vector field, which will be a determinant of ijk, partial x, partial y, partial z. And I'm rewriting all the components of the vector field. So I will have, for the first component, I will have, let's write it as determinants, x, y, z, and minus y squared, minus j partial x, partial z, xz minus y squared plus k, partial x, partial y, xz, xyz. So we will have the cross product with a plus. So rather than a product, actually, what we are taking as a derivative, so we'll get minus 2y minus with respect to z xy. Then here, with respect to x, nothing. Respect to z, just x. And then with respect to x, we'll get yz. With respect to y, nothing. So the components of the curl will be minus y can be taken out, so we'll have x plus 2 for the first component. For the second component, we just have x, and for the third one, yz. And that's the curl of f. So we can say curl of this vector field is this expression, this vector. So to summarize, given the vector field, the curl produces you a new vector field. And what does it have in common with the original one? Well, we'll understand it slowly, but first, so the hint has, as the name suggests, it has something to do with rotation. But let's first notice that if we look at the conservative vector field, the one given by the gradient, then we will see that the curl of that will be 0. Why is that? Try to put the video on pause and prove it. But after you come back, you will see that so curl of gradient f, why should it be 0? Let's see. We'll have to take vector product with the gradient. So that means that we are doing ijk, and here we have dx, dy, dz of what? Of df dx, df dy, and df dz. So we will have, for the first component, d dy of df dz minus d dz of df dy. For the second, I will abbreviate now partial x of df dz, so second f dx dz with respect to z of df dx, so second partial f of dz dx. Finally, plus k will have the same for second partial y, xy minus second partial f yx, dy dx. And provided that your function is well behaved, in other words, if conditions in the Clairaut theorem hold true, that is, f has continuous second partials. So we can say abbreviate it like this. F belongs to C2. That means second partials are continuous. Then by Clairaut theorem, all of the above components are 0. Is 0, 0, and 0. In other words, curl of this conservative vector field is equal to 0, which gives us an interesting criterion for finding out when our field is not conservative. So if the curl is not 0, then we know the vector field is not conservative. Interesting question is, what can we say in a different direction? Can we say that if curl is equal to 0, does it necessarily imply that the vector field is conservative? Not always, but as we exactly the same condition under we saw similar question answered in the positive for plane vector fields, if your domain is simply connected, doesn't have any holes, and any 2 points have a path connecting the two, then you can answer this question in the positive. In other words, if the curl is equal to 0, then function, the vector function, vector field, is necessarily conservative. You can start looking for that gradient. Okay. So here's a quick physics interpretation without going deep into it. We'll understand it after we formulate the corresponding theorem, which is an analog of fundamental theorem of calculus for double integrals. We will say that curl represents a rotation. So either rotation in the solid body, or if you imagine the fluid flow, then you can see that if the curl of the fluid flow is non-zero at some point, that means that there will be a tendency to rotate in the of the fluid around this point. So in other words, if you let's sail a small tiny paddle wheel, then if it comes to this point, then given that the curl is not zero, it will be rotating. While if the curl is 0 at this point, then it will be just moving without rotating. And we'll explain why after we understand the corresponding FTC, corresponding fundamental theorem of calculus for these integrals. So in this case, if the fluid has 0 curl at this point, then we'll call it a rotational at P. Otherwise, this paddle will rotate. Okay, couple of words about divergence. So divergence, sometimes written like that, divergence of F is just equal to gradient understood as an abstract vector dot your vector field, dotted with your vector field. So in other words, you will have dx, dy, dz dotted with your PQR, and the formula becomes dp dx, right, plus dq dy plus dr dz. In other words, divergence takes as an input a vector field and produces a function, produces a scalar, dp dx plus dq dy plus dr dz. That's a scalar function. Of course, it depends on x, y, and z. So let's take a look at the example. So what if we have the same exact vector field? Now we want to find divergence. So we'll get a function. So xz, xyz minus y squared. Okay, let's take divergence of xz, xyz minus y squared. Then we'll get a partial with respect to x of xz plus partial with respect to y of xyz plus partial with respect to z of negative y squared. So the first one will just give you z. The second one with respect to y will be left with xz, and here you'll get 0. So z times x plus 1 is the final answer. And you see it's a function. Okay, scalar function. So starting with the vector, after you apply divergence, you obtain a scalar function. Okay, what is the physical meaning? Physical meaning have to do with, again, just the name suggests, with emergence of matter, let's say you're looking at a fluid, out of a point at which you consider the divergence. But if such divergence takes place, if divergence is not zero, then we'll say that this is a compressible fluid. And if divergence is positive, then we'll call this point a source. So a similar theorem will tell us that if you apply divergence to a curl, so you're taking the gradient vector, then dotting with this cross product, then you'll get zero. Zero vector, zero scalar. Of course, zero scalar. So is there a shortcut to proving this? Or do I have to write again big matrices? What is the shortcut? Can you find it? Pause the video and think for a shortcut, about a shortcut, but the hint is shortcut to showing that divergence of curl of f is zero is thinking about that really as vectors. So if you are doing the dot product, this is understood as vectors. This is just determinant of first vector understood as a row, second vector as a row, mixed triple product, right? Third vector understood as a row in components. So you know in the determinants, when two rows are the same, then the determinant is zero. So you can just refer to the property of determinants. Well, this is a little bit informal, but so I encourage you to do the complete calculation of this determinant and see that it is zero. And of course, you'll have to use some property. And guess what? It will be Clairaut again. Okay, so physical interpretation is a gas or flow of a fluid is incompressible when divergence is zero. And otherwise, you'll have things come out. So divergence basically will measure the amount emanating from a point or being lost. The fluid will sink, will disappear at the point. So if there is some positive divergence, then we'll say at the point P. Then we'll say P is a source. Otherwise, we'll say that P is a sink. And again, we'll understand why it happens and how to explain this later. Maybe last word is that divergence is related to a famous Laplace operator, which you as an engineer will deal with likely a lot in your career. So if you apply it to a gradient, so you can apply it to a gradient, of course. So if you are taking the divergence of a conservative vector field, then what do you have to do? You have to let's write it down in detail. So you have to do ddx of df dx, right? So the first component plus apply ddy to the second component df dy plus ddz to df dz when you're doing the dot product. Hence, you will get second partials. And the traditional notation for this is like this, delta, Laplace operator. So Solutions of Laplace operator are known as harmonic functions. So Laplace f is 0, hence f is referred to as a harmonic for short. And those play a big role in signal transmission. So radio waves, very, very important for applications. So you can apply Laplace to a whole vector field, but then we'll just understand that by default, that would mean applying Laplace to each of the components, P, Q, and R. Okay, that's all for today. We'll talk about how to relate these operators with Green's theorem in class next week. See you in class.